Welcome to Zero Knowledge. I'm your host, Anna Rose. In this podcast, we will be exploring the latest in zero-knowledge research and the decentralized web, as well as new paradigms that promise to change the way we interact and transact online. This week, I chat with Dankrad Feist, a researcher at the Ethereum Foundation. We talk all about the future of the ETH client infrastructure, the merge, Verkle tries or trees, and more. We also explore how concepts that originated in the ZK research space have made their way into the ETH client stack. But before we start in, I want to let you know about ZK Hack, a multi-round online event with workshops and puzzle-solving competitions. It's put together by this podcast and the ZK Validator, and it's supported by a group of fantastic sponsors. It will kick off a weekly cadence starting October 26th. So every Tuesday, we'll be hosting a workshop and a puzzle. Think hackathon meets CTF meets round-based competition. There will be a leaderboard and there will be prizes, as well as deep dive learning sessions with the best teams in the space. Do head over to the website now and sign up to join. I've added the link in the show notes. I also want to thank this week's sponsor, Aleo, who, as an aside, is also one of our partners on ZK Hack. Aleo is a new layer 1 blockchain that uses cutting-edge cryptography to achieve the programmability of Ethereum, the privacy of Zcash, and the scalability of a rollup. It's gas-free and gives developers the tools they need to build programs to protect privacy while allowing applications to be regulatory compliant. The same team has also built a new open-source smart contract language called Leo. This will enable non-cryptographers to harness the power of zero-knowledge proofs to build next-generation private applications. Applications like front-running resistant decentralized exchanges, hidden information games, regulated stablecoins, and more. Go to aleo.org to learn more about the protocol, or roll up your sleeves and visit leo-lang.org to start building. And last but not least, the Aleo team is inviting the community to participate in their ongoing setup ceremony for trustlessly generating the system parameters. You can find out more at setup.aleo.org. So thank you again, Aleo. Now here is my episode with Dankrad. So today I'm here with Dankrad Feist, who's a researcher at the Ethereum Foundation. This is the first time Dankrad's on the show. I want to say welcome to the Zero Knowledge Podcast.
Hello, and thanks for having me.
You are not, however, the first Ethereum research person that we've had on the show. We've spoken to Justin, we've spoken to Vitalik. I feel like we've spoken to a few other of your colleagues. But I'm very curious to hear, what exactly are you working on in Ethereum research?
Yeah, I'm working on fundamental protocol research things. So I'm working a bit more on the theory sides. So I do a lot of things that have to do with cryptography. Like I look for new cryptographic constructions that we need in our protocol. I work with the cryptography team at the Ethereum Foundation. And yeah, I'm basically the interface between the protocol and the cryptography, finding new constructions and putting them into our specification.
Would you say, or is your primary focus ETH2 then? I know that there's been some debate as to whether or not it should even be called ETH2, but like at the ETH2 world as we've understood it, is that where you are focused?
So this is how I originally came into research. We are actually now giving up this distinction because it doesn't really make sense anymore. Like the merge is coming up, and from then on, like it will all be one. So it will all just be Ethereum research.
Yeah. And
I have actually now started doing work that's like, I guess the distinction is now between consensus and execution. Like the consensus part is what used to be ETH2 and execution is what used to be ETH1. But I'm also working on execution things. So for example, statelessness is all about execution, and I've started working on that earlier this year. So I'm doing both, I would say.
Got it. I had an episode with Ben Edgington, I think a few months ago, and in that, like, we explored this evolved version of ETH2 and the merge and the two different kinds of nodes or two different kinds of agents in the Ethereum construction. I would love to at least briefly cover that again for this episode, because I know that we're going to be talking about like these different roles. And I want to explore kind of both of them with you, if that's possible. So yeah, can you explain to me, or can you explain to the audience, like, how does future Ethereum look like?
Right. So currently in Ethereum 1, as it is now, we have clients like, for example, Go Ethereum or Open Ethereum, and they actually have several different roles. They verify the consensus, so they verify that they are on the chain with the majority hash power, but they also verify the correctness of the execution. So they execute every single block and confirm, oh yes, like all the transactions were valid, and this is the new state root that resulted from that. Compared to that, so in ETH2 currently, we are already running the beacon chain, but we aren't actually doing any execution on it. So right now, that's more or less just a way to test out the consensus. And this is, of course, the new proof of stake consensus, which, to be fair, is a lot more complex than proof of work to verify. So like it's very reasonable to test it for an extended period, but it does nothing else at the moment. And once we merge the two, we are actually planning to keep the separation between these two kinds of clients. But what is currently the ETH1 clients, which are going to be execution clients, will not care about consensus anymore. They will then, their only role will be to verify correct execution, and they will leave the verifying the consensus, the proof of stake, to a different piece of software, which is what is currently the ETH2 client.
You just mentioned beacon chain, though. Is the beacon chain the ETH2 client?
Yes, so that's basically what ETH2 clients do right now. They just follow the beacon chain.
So you just said the beacon chain has no execution currently, but it sounds like, will it ever have execution?
Well, basically what is currently Ethereum 1 will just become part of the beacon chain. So we'll put the ETH1 blocks, which currently come with proof of work as consensus, we'll put these onto the beacon chain blocks, and that will be the execution. But then whenever an ETH2 client, what's currently an ETH2 client, let's call it like consensus client, receives the beacon chain block, they will immediately send this execution part to the execution client, let it verify, and then they get a message back, yes, this was correct, or like, no, you shouldn't follow this block. It's not a correct block.
So as I understand here, though, there's two different client types, but there's only one chain. It's not that there's two chains running parallel. And you sort of said that there's this verification, like what is actually going to be written then onto the chain? You sort of said this execution would be written on, but like, what does that mean? Like, what does it look like? Is it just a proof or something?
It looks the same as a current ETH1 block. So currently ETH1 block consists of transactions, and it also has a state root. So like basically at the end, when you've executed all those transactions, you commit to like, this is the new state. And basically like the execution is verifying that these transactions lead to the new state root.
What are you calling what was the ETH2 client now? Is that just the consensus client?
Yes. So that's what it's going to be in the future. Yeah.
Okay. And this is going to be proof of stake. So this is where the validators are going to live. I guess this is where the current validators already live. It's just going to be evolved a little bit. Why the separation?
Why we're keeping two kinds of clients. So, I mean, in practice, we've already seen, like with Ethereum in the past, that the monolithic design, like having one big client, leads to like a lot of problems. Basically, like teams don't scale very well. Like typically, like developer teams work best when they're like small teams, 5 to 10 people or so. It's really efficient. But once you have like a big monolithic piece of software that requires a larger team, like things become very problematic. And like basically, generally, like the ERP process was slowed down a lot because of this, because it's just like, I mean, actually, we currently only have like one team that was able to really keep up with it. And that's like a huge problem. Like we're looking toward this multi-client feature where we don't have to rely on one single client that ensures consensus. Like we want to have a fail-safe. If one client has a bug, then there's a different one that we can rely on that will correct it. And this can only work when you have like smaller building blocks where like you can put different pieces of software together and they can live independently, maintained by independent teams that only have like a limited interface where they need to work with each other.
And that team you were mentioning, though, the one that's running right now is Geth, I guess.
Exactly. Yes.
Yeah. Okay. And I mean, we did talk about all these clients that are building the consensus client, but are you also expecting more teams to start building the execution clients?
I mean, that is happening. Like, we do have other clients which are currently in the process of catching up. So, I mean, I believe that this will happen. One major feature that we're working on that will enable this more is actually statelessness, because that will enable different sort of sets of features that execution clients can target, and some of them will be much easier than others.
That's a topic that I want to jump into, like, kind of in depth. But I first still, like, I kind of want to understand, or I want to make sure that we're super clear on these, like, two clients. And I think I want to know a little bit about the consensus side first. Specifically, like you were saying, you used to work there, or you used to work more on that, focused on that piece of the stack. Is there ZK stuff in the consensus in ETH2? The reason I ask is I've, like, having seen some of your talks and, like, obviously having followed ETH research for quite a while, like, zero knowledge concepts keep getting, like, put in. But in this final version of the client, the consensus client, is there anything zero knowledge in there?
So the answer is not at the moment.
Okay.
It's something like, I mean, it's really when you're working on something as fundamental as, like, the consensus for the future of Ethereum, then you have to be quite conservative. And so we don't want to use it unless we're really certain that we both need it and that we are really sure that it's safe and everything. Mm-hmm. So there's a very high bar, and we really want to keep things simple. There are pieces, however, where this might happen in a relatively near future. Like, one is so-called single secret leader election, where we want to make it so that only the block proposer of a block knows when it's their turn. Like, currently everyone knows who's going to be the next block proposer, which causes some problems. Mm-hmm. So basically the problem is that you can then DOS that specific validator, even if it's not currently known which IP is behind which validator. There are probably ways to find out if you're really, like, determined. And so single secret leader election avoids that, because you won't know who is going to be the proposer, so you can't DOS them.
Is that an idea, or is that something that's already built in?
No, so that's not built in. We currently have a protocol that I think Mary Moller was working on, and that's now, I think, like, I mean, we know it works and everything. As far as I know, there's currently a team working on that, on speccing that out and building that out. But it's going to be at least a year or so, I would reckon, until it would be actually implemented.
Are you then going live with the consensus client as it is, where that could happen, where, like, a validator could actually be doxed?
Well, I mean, it's already live, to be fair. But yes, like, the immediate version after the merge will have that. But I mean, like, as I said, it's not that trivial. Like we don't have a public list, like, which validator is, like, which peer-to-peer nodes. So you would have to be quite elaborate and, like, set up, like, a huge dragnet in the peer-to-peer network to find out who you have to DOS.
Okay.
It's possible. And then there would still be ways to react to this. Like, you could then put nodes behind Tor and stuff like that. Yeah, we want to fix it, but it's also not, like, something where I immediately see that there will be huge attacks.
Got it. What kind of consensus is it? So we talked about it being proof of stake, but what is it based on? Is it different from, like, Tendermint or from the Polkadot model? Like, is it very unique?
Yes, so it is different from what many other consensus protocols do. So it's the Casper FFG protocol. So, of course, one thing we want from proof of stake, which is something that proof of work can't give us, is finality, like this property that you can have a checkpoint that can never be reverted unless at least 1/3 of the validators collaborate to do that, and then they would also get slashed, so they would lose a huge amount of money. But we do want more than that. So, like, basically, we're not happy with the property, like, that traditional consensus protocols have, that, like, once you have less than 2/3 of the validators online, that you can't build a chain at all. So we want, in addition, we want what we call this available ledger. So even when more than 1/3 is offline, we can't have this finalization property anymore. We know that. But what we can still have, we can just build, like, an optimistic ledger and keep building a chain. And, like, some people might be happy to work with that and some others not. So that's your own decision as a user. But, like, basically, you're not just stuck with like nothing. And that's something we really want to do. And so like that's why we have a different protocol that's quite specific to Ethereum.
Got it. So now let's move into this execution client side of things, because I know you had mentioned statelessness, and I know I wanted to explore this a little bit. The execution client, this is the current, it's like the Ethereum client as it's known today. This merge, as I understood it, it's like it will be somewhat seamless for the client runners. They download like an update. Tell me a little bit about how, from the client side, like the ETH1 clients, as they are run today, what changes?
So it will not be completely no change at all. It's not just you are, because of the separation that we're doing between execution and consensus clients, it's not enough to just update your client. So basically you will have to run an ETH2 client as well, because you need to verify the consensus size of things as well, which currently the ETH1 client does, but in the future won't be able to do anymore, because that depends on the beacon chain, and people aren't going to implement that in Geth, for example. So basically for someone who currently runs an ETH1 node, they will need to pick one of the ETH2 clients and run that in addition to their current ETH1 client and connect the two so that they can keep running ETH1, an Ethereum node. Yeah.
Can someone just run the consensus? Like once this is all live, if they just want to run the consensus node?
No, you can't. And that's because the consensus is only valid if it's based on valid ETH1 blocks. Basically, it's always like, this is always the property that we want with blockchains, that you both verify that a majority is voting for your current chain, but also that it's a correct chain. And it's only a consensus if both of these properties are true. And you can only verify the second part if you also run this execution client. So you always need an execution client.
On the actual merge, what happens to the previous ledger? Like kind of that big chunk of data that everybody needs to have on their computer, will that just stay somewhere and then a new?
No, it just becomes part of the beacon chain. So,
okay.
So the whole chain the two chains just come together, like the opposite of a fork in a way. Yeah.
The merge. Got it.
Yeah, exactly.
Okay.
Yeah.
Okay. So in this execution client, this is maybe where I sometimes get a bit confused, because I thought I knew that there was these two clients. I thought of it as like maybe something you could run separately, but it sounds like no matter what, you're going to be running both all the time.
Yes.
It's
pretty much. Yeah.
So it's kind of like running one, but it's under the hood, there's going to be two.
Right. And you can pick and choose. So yeah, like we're planning to make this all compatible. So you can run all the different combinations of execution clients and consensus clients.
Okay. All the different teams who've built their unique clients. Do you think, will these clients have very unique properties? Like between teams, like will they be able to actually have different qualities? Will like MEV still be like only in some of them? Or not MEV, but rather like a Flashbots like project in only some of them? Like that's sort of what I'm curious is like how heterogeneous is an execution client?
I think it's similar to how it is now. Like different teams can focus on different specific use cases. Like, some teams might decide that they want to build a really lightweight client that you can run on very like low hardware. Some teams might decide to run on mobile phones, which I really encourage, which is great. Like if we can do that. And others are maybe focusing on enterprise, where we can integrate with everything and maybe focus less on resource consumption because that's less of an issue. So I expect these different kind of strategies to exist. But I think that's more or less the case now, except that like at some point, I guess like in ETH1, many client teams dropped out, unfortunately, yes.
You just said that you could potentially run it on a mobile phone, but you still need to have this heavy chain, don't you? So like, how would that work? Do you have to break it up somehow?
Okay, there are different things here now. So right now, for example, the consensus, the beacon chain, you could easily run that on the mobile phone. I don't think like most mobile phones would be capable of doing that.
But that's current beacon chain before the merge.
Yes, exactly. So after the merge, I don't actually know if it's possible now. It would be an interesting thing if anyone has tried porting. I'm not aware, but I would say like a good mobile phone could probably run currently an execution client, because like they mostly do use SSDs anyway. And the main restriction, like you can run execution on Raspberry Pi. but you need an SSD. You need to add an SSD to it. And this is actually the big thing that's going to change with statelessness. So after statelessness, it's going to be easy, because you don't need that SSD anymore. I would suspect it's possible to run it on a mobile phone now. I think it's a bit challenging.
Okay. What is statelessness? And just as a caveat, I'm pretty sure I've talked about this on the show before, but it's been a while, so I don't remember.
Right.
So maybe you can help me to just tell me what statelessness means, and maybe what is statefulness? What's the opposite?
Yes. So, there are different degrees of statelessness. I wrote a blog post going into details about these, but basically what we're aiming for is so-called weak statelessness. And what that means is that you can verify the execution of everything. So these execution blocks that we talked about earlier, which consist of basically transactions, and then a new state root. And you can verify that all that was correct without having any additional information. So basically, in terms of pure, I guess, computer science speak, we would call it it becomes a pure function. So verifying that a block is correct is just you just take that block and it's true, false. You don't need any other inputs. There's no nothing that changes with it or anything. That's it, right? What we're aiming for is weak statelessness, which means only the verification can be done without the state, not creation of blocks. In order to create new blocks, you still need the state. There are reasons why we think that's fine, and that's the best way of doing it in terms of UX. There's a stronger notion where you say even creating blocks should be possible without the state, which would be the strong statelessness.
But currently it's, and I don't think you call it statefulness, but it's not transparent. You're still verifying state in the current thing, right? It's not just
So right now it's stateful. Right now, in order, if I send you an ETH1 block and ask you, can you tell me if it's valid or not? You would need to have this whole tens of gigabytes if Ethereum state, otherwise you can't see it.
Got it.
And basically with statelessness, what happens is we add these witnesses, these proofs that everything in this block had a certain state and this was applied correctly. And we add that to the blocks, and then I can send you this block, and without knowing anything else, just by putting it in a piece of software, you can say this is a correct block or this is not. Even if you don't even know the previous blocks, you might never have heard of them. It might just be one isolated block and I don't even tell you what happened in the past.
What is this witness? Is a witness a proof? Is witness an agent? Is witness a client?
A witness is a certain kind of proof.
Okay.
It's a proof of correct state access, basically. So basically what will happen is with statelessness, so for example, one operation that I could do is I transfer 1 Ether to Anna. And as part of verifying that transaction, you need to do certain things. You need to verify Dankrad had 1 Ether. Mm-hmm. You need to verify after executing this transaction, he has 1 Ether less and Anna has 1 Ether more. Yeah. So, and there are a couple of more things. You also need to check that the signature is correct. So you also need to know what is my public key. And you need to know that this transaction was set in the right order. So you need to know my nonce. So these are basically the different things. And all of these things, this information, we will add to the block. So each of these pieces of information, instead of getting it from your memory when you verify the block, I just provide them to you as part of the block. Mm-hmm. But in addition to that, now I have to prove to you that I provided the correct information. Mm. And so that is the witnesses. That's the witness. So the proof that these 5 pieces of information that I just mentioned, that will be part of one such transaction, that all of these were provided correctly, that's the witness. Then a nice property of these witnesses, at least in the scheme that we are using, which is Verkle tries, is that using this witness, you can always also update this information. So now we have the state root, and now we need to compute an update to the state proof. So there's a pre-state root, that's the commitment to the complete all state, all accounts, everything that Ethereum has. Mm-hmm. And then we have an update state root, and that says this is all the new, this is how it's after applying this block. And we need to verify that's correct. And the nice thing is the witness gives you all the information to update it. So now, from this witness, I can also compute, okay, these are all the changes that this transaction enacts. And then, we verify that these were correctly applied to the state root.
What kind of proof is a witness?
Well, I mean, it's, for example, if your state commitment scheme would be a Merkle root, then it's a Merkle proof.
Okay.
So it can be different. It depends on your commitment scheme.
But in this case, then it's like, it's not, because I guess when you said it's a proof, I started to think, is it a zero knowledge proof or a fraud proof? Or so, like, I started to think like validity proof, like, is it?
Well, and it could be a zero knowledge proof. For example, like there's the notion of witness compression where you say, I want this witness to be as small as possible. And then you can simply have a zero knowledge proof that shows that your witness is correct. And then you don't need all the witness anymore. And like in a way, like when you look at how Verkle proofs work, it employs a lot of the technique of like general zero knowledge proof. So yeah, in a way, it is a zero knowledge proof.
Is this in any way, and I don't know if you're as familiar with like the Mina system, but like the idea of recursive snarks being used as validity, like does it in any way relate to that, or would you see this as quite different?
No, I mean, we're not trying to compress the execution. So we haven't touched execution at all. Like to verify the block in a stateless system, you still need to actually execute all the transactions. Basically, the elegance of statelessness is like realizing that executing is actually not a big deal. It's not the main problem. And also downloading all the blocks is not the biggest problem. The biggest problem with execution, like with smart contract execution as we have it right now, is accessing all the state. If you look at what the big problem of running an Ethereum node is, it's all about every transaction touches like different parts of your, so you can't just, it's too big to just keep it all in RAM. But once you put it on a hard disk, it just becomes very, very slow. And that's the big deal. And that's why statelessness goes such a long way. Of course, like basically proving the complete execution is strictly more powerful. Like it's much better, but that's also a much, much harder problem. So we see that definitely coming in a few years, but statelessness is like a great step in between that gets us many of the advantages already.
Does this impact data availability itself, or would you put that in a different place? Like when you talk about having to prove and trace back, like that's at least what comes into my mind, but I know it might be a different part of the thing.
Yeah, so data availability is quite different. It might sound like the two are related, but when we're talking about data availability, we are like the main thing we're trying to solve is this data withholding problem where someone tries to hide some data. And that's not really like a concern with the state. So they're two quite separate problems.
I see. And the statefulness, when we like here, we're still talking about, I mean, and I know that the question of data availability comes up a lot because of like the L2s and the rollups, which I believe would intersect with the execution client, right? Not with the consensus client.
They can intersect with both because when once we add sharding, well, I guess that's a debatable thing, but yeah. Maybe so sharding will probably be part of what is currently the consensus client. Yes.
I'm almost wondering if we should hold because I have more questions on the L2 side of things, but let's keep going into this. So you had just mentioned Verkle tries or Verkle trees. I know tries and trees and Verkle is a take on Merkle and vector.
Yes.
I'm assuming Merkle.
Let's take the word completely apart. So basically, like Verkle try, there's like a lot in these two words. And basically, Verkle stands for vector Merkle. So it's basically a combination. It's a Merkle tree, but with a vector commitment instead of a hash at the nodes. And try simply means it's a kind of tree. And it's just a kind of tree that's used for key value storage, where you just use a key to determine the path. You use your key to determine the path you go through your tree. So that's what the word is about. And vector commitment. So vector commitments, what we're looking for is efficient vector commitments, basically, where you can prove membership with less than linear work. So for example, if you hash like 16 children, right?
Are they called leaves sometimes?
So the leaves are at the very bottom of the tree.
Oh, okay.
And then nodes are anywhere in the tree, and nodes have children. And they can be leaves or they can be other inner nodes, right? So both are possible.
Got it.
Yes. And then each node has children. And in the Merkle tree, you just hash all the children. And in Merkle tree, you usually have exactly 2 children per node. And the reason is that this is how Merkle trees are most efficient in this way, because in order to prove membership in a hash, you have to give all the siblings, right? And so if you make it wider, then you have to give a lot of siblings. That's the problem with a Merkle tree. So there's no point in making it wider. It becomes less efficient. But if we use efficient vector commitments, they are inefficient. Like a hash is technically a vector commitment as well. It's just a bad one because you have to give all these siblings. So we're looking for more efficient vector commitments, which luckily exist. And then we don't have to give all the siblings. We just have to give a constant size proof. And suddenly it makes sense to make them wider because suddenly that doesn't increase the proof size anymore. It just decreases the depth, which decreases the total proof size. So that's why we want Verkle trees.
One side note, I mean, you did a talk quite recently on this with graphics, which I will link to in the show notes because I did watch that. So I'm following what you're saying, but I'm also realizing that if people are just hearing it, it might be a little bit, it might be good to just see the map, to see these trees kind of mapped out. But anyway, sorry, continue with the explanation.
Yeah. So like basically now you could ask the question, like, why don't we just go to like width infinity? Why don't we just put it all into one vector commitment if we have them? Because that's great. And the problem with that is that this would be amazing for the verifier, like whoever just wants to like verify that the witnesses are correct. But it's very bad for the prover because all these vector commitments, basically once the width becomes very wide, you need all the siblings for the proof. You don't need them to verify it, but you need them to generate the proof. So basically the Verkle tree is actually an interpolation between these two extremes where you kind of make a trade-off between, okay, like we give the verifier a bit more work, but in return, now the prover becomes actually like practical.
Crazy. Who makes the blocks in this entire setup?
Right. So I'm assuming you're talking about the execution blocks. They would be completely remain the responsibility of execution clients.
Okay.
And post statelessness, you can have different goals with an execution client. For example, you might say like, I only want to verify consensus. I don't actually care what the actual state is. And then you will run a stateless execution client.
Just verify.
That just verifies. Okay. So it will never generate a proof. And like you could ask the question, well, what's that good for? Like as a user, like don't I need the state somehow, or at least need my account or something, or the contracts I interact with? But the nice thing is actually, I think it's extremely useful because suddenly you can just get the actual state from a service, but you don't have to trust that service anymore because you can very, very easily just verify that everything's correct just by doing this much, much less expensive thing. So suddenly, like Infura doesn't become this, horrible centralized thing that everything in Ethereum depends on. But it's like, well, you just run this tiny extra piece of software and Infura becomes powerless. Like they're just a service provider and like you don't have to worry about them cheating or anything anymore.
Yeah.
You might have to worry about them going offline, but once we have a couple of these services, that shouldn't be a problem either.
Okay, now the other question is who makes the proof?
Yeah. So basically, in order to create those proofs, like when you create a block, you have to create the proof. So as I said, we're going for this weak statelessness notion where you transactions don't come with their full witnesses. There are several reasons for this. It makes a bit less sense to do this in a smart contract chain in general. So basically, we're doing this weak statelessness. The block producer, in order to combine the transactions, they have to have the full state and they generate the proof. This is not like, it's not horribly expensive. Like, I mean, I've done some estimates and like this should be like a few seconds of work or so at most. So it's actually really easy, but it needs the state. So it's not much worse than running a normal ETH1 node now. So things aren't actually getting worse for block producers.
You just made me think though, like I always equate validators as block producers. And in this case, is the block producer living only on the execution side?
Right. Yes. So there's the beacon chain.
Yeah.
And the validators are the block producers for that beacon chain.
Okay.
And it doesn't make much sense to like do that any differently. There's a difference for the execution chain. So the execution chain, when you run your own execution client, you can make that produce your blocks for the execution chain. What we're seeing in practice, though, is that because of MEV, like a lot of people very likely will outsource this functionality. And this probably is the most efficient construction. And so like we're not going to stand in the way of that. So very likely, like the actual proposing of blocks is going to be a much more specialized role that like people who extract MEV are probably going to do.
So wait, I got a little lost here because you just said like there's block production on the execution chain. I know right now there is, but like, is there actually block production on the execution side?
So it's just this part of the block. So like the beacon chain block, the full block will be everything that is now, just the consensus part, and will contain basically one field that is like execution block. And I'm talking about this field. So that's what I mean by block production on the execution side. So it's not a full block. If you just send that on the peer-to-peer network, it would be ignored because that's not anything it's
not fully
anymore.
Locked in to the beacon chain.
Yeah, exactly.
And now going kind of back to what we were talking about before, the proof generation, this witness proof, would be made on the execution side into the execution block that would eventually be included in the beacon chain.
Exactly. Yeah.
Full. And would be written into that chain by the validators.
Yeah.
Okay, cool. That's helpful. Yeah. You said weak statelessness, and the word weak, I know you've already said how it's weak, but I want to kind of highlight what's weak about it.
Yeah, so weak just means block producers still need the full state. That's what it means. That's how we define it.
Okay. It's stateless, but you still need the state. It's
I mean, in the end, let's say it like this. Someone always needs the state, right? And I guess like the strongest notion of stateless is like
nobody needs the state.
Well, no. The strongest would be only the users maintain their own state. Like you have an account and you will always just remember how much you have in this account, and you remember your witness for your account as well. I think that's terrible for UX because like it means you always have to be online. Otherwise, you always have to be worried. What if I go offline? Like, I will. Someone sends me something, and now the problem is you have more ETH, but you have no way to access it anymore because you always need a witness to access your account. So that sounds pretty bad to me. I don't see how the UX of that is attractive. Does this mean that block production is maybe a bit more centralized and like not as decentralized as the validators? And I think this is likely true, but this is will be forced by MEV anyway. So that's very likely the case. And the reason that I'm not that worried about this is that we only need one honest block producer in order for this to be fine. Like we only need someone to still be online and not to be censoring. For the system to work. Whereas if we look at the validator set, the full validator set, if a majority of them is compromised, then we have a problem, right? Like basically everything breaks. We don't get our nice guarantees anymore. But this is not true for block producers. Like we just need one of them. And like if we notice, oh shit, like they've all gone to shit, then someone can just make a new one. And they don't need to like replace everyone else. Or so they just go online and say, here are the new blocks. I'm here now. Just take mine. So it's a much weaker security assumption. And I think that's amazing. And that means that I'm much less worried that there's some reduced decentralization in that part of the system.
So what you're saying here, though, is it has a weak security model. Does that kind of almost mean like
Well, the security model is actually stronger because it has a weaker assumption. The assumption is weaker, so the security becomes stronger. Yeah.
Okay, so but like if the assumption is weaker, then what you're saying is, do you need less in order to be secure? You need like less good actors? Is it like, I'm kind of going back to the validator idea. Like, is it now saying like you only need, is it like an MPC? You only need one honest participant in order to like actually have an honest system?
Yeah, exactly. Yeah. That's basically what I'm saying. Yeah. So like, it's this N-1 security assumption. Like as long as there's one honest party, everything's fine. Everything works.
Yeah. I don't know if I fully understand how that works though. Like why can one honest proposer actually like beat out the others?
Right. I mean, the assumption would be like, so for example, in what we call like this builder proposer separation, we say like we basically have two different roles, like one where you build blocks and a different one where the validators, they pick one of those and propose it. And then you need a certain system to protect the builders from just taking their blocks and taking them apart and proposing them in a different way. But we have systems to do that. So the idea is basically the builder will bid for their block to be included. They will just bid for their whole block. And so like they can make this bid based on the transaction fees that they're receiving and on any MEV that they can extract from it. And then the proposer just needs to take the highest bidder.
Oh, wait, the proposer, like the builder. I think I confused them. I thought the proposer fed into the builder, but what you're saying is it's built.
No.
And then the proposer.
The builder is the one who assembles the blocks, like chooses transactions and say like adds new ones to extract MEV and stuff like that. And the proposer is just the one who like says, I propose that we choose this specific block from the builders.
I see. And they don't earn any fees necessarily, do they? The proposer.
They basically, so the builder will pay the fees to the proposer. So basically, in the end, actually, if it's competitive, then the proposer should actually receive most of the fees and the MEV, because like if there's two different builders and they're both quite good at extracting MEV, then they will constantly outbid each other, like bid a bit more, because like they basically their limit is however much they are gaining from the block. Right, so it's this competitive market, and all the profits should in the end go to the proposer.
Oh, I misunderstood that then, because the builder itself, like putting this together, if they're doing the MEV, like they're incentivized by fees, as far as I understand, like or I guess fees and arbitrage. I don't know, fees and Flashbots payouts, fees,
exactly,
but like
exactly.
So is that what you're saying though? Then like the builder will be more incentivized probably by the MEV side of things and less by the fees.
Both. I mean, both. Fees are a type of MEV, right? So all the fees that go to the block producer, builder, proposer, they are also MEV, right?
Okay.
Because they go currently what we call to the miner.
But I'm still confused though. Like, what I just understood though is fees kind of go through the builder to the proposers. Like the proposer.
Right. But the mechanism is not direct. So like basically, I as a builder build the best possible block that I can build. Like the one that gives me the most possible amount of fees, MEV. Call it all MEV. Basically MEV, because fees are actually part of MEV, right? Okay. Now I have this block. Now I need to bid for a proposer to include this block. Mm-hmm. Right? How much am I going to bid? Well, the maximum I can bid is however much MEV I'm getting, right? I'm not going to bid more because then I lose money.
Yeah.
Okay. The minimum is I have to bid more than anyone else. Otherwise, I won't get it included.
Yeah.
Right? And so as long as there are two reasonably good builders, they will raise the price to almost the MEV, right? They won't pay as much. They will pay a little bit less. But if it's competitive, then they would pay like only a little bit less, and that however much less, that's basically their profits, and but most of it would actually go to the proposer.
And the proposer is the kind of agent that you imagined being more professionalized and potentially more centralized.
No, the builder.
The builder is more okay.
Yes, exactly. Yeah. So the proposer is the validator. The proposer is just a normal validator.
Yeah.
So, but the point of this is that we don't want validators we don't want them to have to become very sophisticated, because that will lead to centralization. If they have to be good at extracting MEV, then they will end up like being only like big pools who are competitive. Like otherwise you're like, well, I don't make as much money. I should rather just join the pool.
Yeah. Is the builder happening on the execution side, and then the proposers, like, is that sort of the crossover moment where it like goes from this execution block to the beacon chain?
So the builder is clearly on the execution side. The proposer is both. Like the proposer is a full consensus client, but that means it has to be connected to an execution client of their own.
Yeah.
But the point is, for example, in the post-statelessness world, that could be a stateless client, which is really, really light. It could be like you almost don't notice that you're running it. It's that light.
I see.
Because you don't need the state, because you're getting the blocks from a builder anyway. So you don't need to run a full stateful execution client anymore, because you never need to build blocks yourself.
But since both clients exist often on the same machine at the same time, is there any way to connect your builder to your proposer?
Yeah, of course, there's. So if you are both good at extracting MEV, or some people might just say like, well, I don't want this. I just want to make sure that everyone's transaction get included and I don't care about MEV, then absolutely you can do that. And yeah, it's possible. Yeah.
Okay, now I want to take another step back to the Verkle tries, because you had sort of mentioned, or you touched on the fact that you're using some sort of zero knowledge techniques in there.
Right.
What are you using? This will be interesting for the Zero Knowledge podcast audience, potentially.
I mean, it's nothing super fancy. Like, it's essentially the way we're building the Verkle trees. I said earlier that they're basically Merkle trees, but with vector commitments. But we are actually using something even stronger than that. We're using polynomial commitment schemes. And basically, I mentioned earlier, so basically the way a Verkle proof works is this. You so you need to give a proof at, like, for every bit of the state, for every leaf that you're accessing, which is basically represents a key value pair. You need to go through all the layers of the Verkle tree until the root, and you always need to give this vector commitment proof. In addition, you have to give the parent vector commitment. So, like, basically, here's a slight difference. Like with Merkle trees, like you mentioned it earlier, you only have to give the siblings, right? Which is really elegant. This is not true for most vector commitments. Like for most vector commitments, the proof itself will not let you generate the parent node, which is the tree for Merkle trees. So you also have to give the nodes themselves, like the nodes on the path. You have to add them to the Verkle proof. And now the bit I mentioned, which is a bit like based on things that you use in zero knowledge proofs, is like to compress this whole proof. What we do is we just use tricks to, like, when you have many polynomial commitments evaluated at many different points, then there's basically a technique to compress all of that in one single proof. And that's a trick that we're using to make this proof smaller.
Where did you get that from? Like, what were you studying that, like, led to that finding?
I don't know. I mean, that's a good question. I think, like, Justin and I have been thinking about, like, polynomial evaluation proofs for quite a while last year. It basically came out of these discussions, but I think Justin basically says it's kind of like a pretty standard technique. So I don't think it's nothing fancy. It's yeah.
We did for the ZK Study Club. We actually did a 3-parter with Justin on polynomial commitments that I'll try to link to as well in the show notes here if people want to find out more about it. One thing we didn't talk about yet was sharding, but I also did talk about it many times on many episodes in the past. I think that our audience should have an understanding of what sharding is. But I guess the question I actually have for you, and this I understand would be happening on the consensus side. Is this on the consensus beacon?
I guess so. I mean, you could actually technically consider it a third part, but I mean, for practical reasons, it will just be part of the consensus client, I expect. Yeah.
Okay. And I guess the question is mostly, is that in the roadmap, or is that sort of been pushed back? Because I know in the conversation with Ben, it sounded like the client developers aren't, like, thinking that much about sharding right now.
I wouldn't call it pushback. I think it was always like an upgrade. I think we decided some time ago that we're going to do the merge first, which I'm strongly in favor of. I think it's a very important part. And, like, we basically need to have that finished before we can implement data shards. So, I mean, in the spec research team, we're definitely thinking about sharding now. So, like, it's not like it's been pushed far away. But, like, right now, client teams wouldn't have the bandwidth because they are all working on a merge full time.
What do you need sharding for in this case? Is this how you scale?
So this is how we scale data bandwidth. So basically, it would add to Ethereum to the functionality to say, this data is available. Like, it was made available. And that's useful because it scales rollups. So basically, rollups need exactly this functionality. Right now, basically, how rollups work, they just put this large chunk of data as call data on the Ethereum blockchain. And the reason they put this is to make it available, to be sure that it's available. And now in the future, they can do this on the shards instead. And on the execution chain, they only have to do like a much smaller piece of work where they say, okay, this was executed. Okay, here's a fraud proof. Yeah.
And this actually, so that going back to that question that I had earlier about data availability, this is the data availability part. So it's not the state data, it's this data.
Yes. Yeah.
Got it. Mm-hmm. I think I was just using like the word data could be lots of things. This actually leads really nicely into kind of my last question of this interview, which is about the roll-ups. Mm-hmm. And your thinking from where you're sitting about them. I think we now live in I want to say post, but not quite. Yeah. We live currently in a roll-up world where we have live roll-ups coming on. Mm-hmm. We have different kinds. We have the optimistic roll-ups. We have ZK roll-ups. We have Validium kind of roll-ups, like the Starkware stuff. So like this has really altered, I feel like, the way of thinking about the future of Ethereum if you compare it to like 2 years ago or 3 years ago.
Yeah.
Are you actively working on almost designing this out? Or is this like the ecosystem builds stuff and then you're kind of trying to find ways to help? I just want to know like where is the research space for you on this?
Yeah, I mean, it's a bit of both. I'm not doing concrete research on rollups, although some people from the research team are doing that. I think like we're more focused on the long-term perspective. Like, for example, like how do we get to full EVM execution, for example? That's an interesting, or like full ZK EVM execution, like executing the EVM in zero knowledge. Like that's still a very difficult problem that I think is a few years away from being practical, but that's definitely one of the big questions. I guess like the nice thing is that, I mean, rollups have basically solved a lot of problems for us. Like, I mean, in the past, I think like a few years back, we were still thinking about execution shards. So like this is basically like the big news that we like completely got rid of them. And I think almost aren't thinking about them anymore. Like they might come back in the far future when we have ZK EVM, but in a way then they are actually rollups.
Wow.
But yeah, so like it has made the design space for us much simpler. Like the consensus just needs to ensure that we can prove that some part of data is available and everything else will be done by the rollups.
That's so interesting. So that's the change then. It was that the execution side of things was going to be sharded, but now with rollups, those are the shards and they're heterogeneous because originally the shards were supposed to be all the same.
Right.
And now you have very different teams even working on these different rollups.
So it's a bit dangerous. So some people have made that mistake of just thinking of rollups as shards. But you have to be careful because one thing that people were super worried about is composability in shards, right? Like that you can't do this anymore. You can't just like call one contract and then another contract and get a complete lock, like getting this atomicity of the transactions. And that's indeed not possible with execution shards.
It's even less possible with rollups, I guess, eh?
Yes, so it's possible within one rollup.
Yes.
It's not possible across rollups. Well, it might be possible across ZK rollups. I doubt anyone will implement it. But the interesting thing is one rollup doesn't have to live on one shard. So if you have many data shards, one rollup can simply live across 10 of them at the same time. So that's the danger in thinking about, like rollups are just a replacement for shards. Well, they are not, because they can fill up, like there's no fundamental thing that restricts one rollup from simply filling up all the shards and giving you full composability across all of them.
Wow. That's interesting. So you really do make a distinction here that these are not like shards. I do wonder, what do you actually see the execution layer looking like as these rollups gain momentum track, like as more actually funds and movement goes over to these rollups? Like if more of the action is happening on the rollups, what is the execution, like the main Ethereum beacon chain in this case, but like on the execution side, what's it for? Like what will it be?
It's the settlement layer. It's like, it's just behind, because like either for optimistic rollups, like you need somewhere to post the fraud proofs.
Yeah.
And so you need someone who can do execution. Or for ZK rollups, you need somewhere to post your proofs and someone to verify this. You could do all of this, which is like basically this lazy ledger, or what is now Celestia idea. You can do many of these things without any execution layer behind. What then becomes very hard, in my opinion, is light clients and settlement between the different layers. So I do think that this execution layer between them brings really advantages.
Why light client? Why does it help with light clients?
Because otherwise the light client still has to, the execution layer kind of, you could almost say like finalizes things in the rollups. And light clients can just take that as their source of truth. And otherwise, they can be light clients on the consensus, but you can't really have light clients on the rollups.
Yeah. You just mentioned ZK EVM too a couple times and how that could change something. Like ZK EVM, we did an episode with Jordi Bailina and David from Hermes Polygon. I guess that's what you call it now. And I know they have a version. I heard after that episode that Ethereum Foundation has a version of ZK EVM. And I think there's a third one that's being built out or developed. These are still very theoretical. It's the idea that you would have like full EVM, like with the opcodes all exactly as it is, but in a ZK rollup.
That would be the ideal result, because then you could just take the execution chain as it is now and put that
ZK
into
it?
the yes.
Oh wow! I didn't think about it that way. Whoa. Yeah. Okay.
So you can't do that if you have any version that requires recompiling or changing the hash functions or stuff like that. If you have to do any of these, then clearly you can potentially redeploy smart contracts to a new chain and do it on that, but you can never do the whole thing on the currently existing chain. So it depends on what exactly your goal is, how far you have to go.
Why ZK EVM? Because you can also have full EVM compatibility and what's the word? It's not even compatibility is not the right word. It's like the actual EVM running as it does in an optimistic rollup. But you didn't highlight that.
Oh, right. So basically what you're suggesting is like take the EVM as it is now, like the execution chain, and instead make it an optimistic rollup itself.
I'm just wondering if there's any disadvantage to doing it that way.
I mean, it's mainly about finality, ultimately, right? Yeah, I mean, I think there are some disadvantages. It's also not easy, to be honest. Like, first, we can't do it until we have statelessness. So statelessness is a prerequisite for that.
Okay.
Then we could, in principle, do that. I haven't thought it through, to be honest.
Okay, fair. But on the ZK side, you have, and so that would be possible.
I mean, theoretically, it's possible. Right now, it's just completely impractical. Like, I mean, the question is like, I mean, you need to be able to generate a proof for a block in seconds, right? And so, yeah, that's difficult.
I do wonder from where you're sitting, do you have a preference for any of the kinds of rollups? And maybe here it sounds more like you've researched maybe ZK more, but like, do you think that it's actually better?
I mean, ZK is better, like for sure. I mean, the optimistic is a practical trade-off. I mean, like, okay, like if I have a rollup with the same throughput cost, blah, blah, and it's ZK is clearly better. Okay. But that's very hard to achieve. So basically that's why we have optimistic rollups, because there are many things we can't do in ZK yet.
And what do you think about like the Porter, ZK Porter, or the Starkware versions, which... Or even actually I guess the ZK EVM uses that even. It's like using a Stark-like thing that creates a huge proof and then using a snark that compresses that into a small proof. But
I mean, I think what you were referring to, like with ZK Porter or like Starkware's Validium, is like having these zero-knowledge proofs for validity, but not posting the data on chain, like basically not ensuring data availability. I mean, there's definitely something in it for ZK rollups, like going to this Validium construction definitely works. Like it has some advantages that like you can't do that with optimistic rollups. I still think that's much, much better to just get the data availability. And I think like with sharding, it will become cheap enough that nobody would make that trade-off. And I think Validiums will just not be very attractive anymore. I think I think ZK Porter is doing this interesting thing where basically... Who's doing this where you basically, they give you as a user, they give you the option to just be online. And if you're online, you just sign that you have received the update.
Oh, I don't know.
And then they don't need to post it online. And I think that's a pretty cool construction, because basically nothing bad happens if you go offline. You just pay a bit more and your state is guaranteed to be online. And if you're online, then you just get it directly and you don't have to pay for the cost of putting it on chain. So I think that's pretty cool.
Yeah, I don't know. I don't remember that from the ZK Poder interview, although it might be them.
No, maybe it was another one. Might be another one. I can't remember right now.
Well, we'll try to find it. Okay, in this world with a lot of rollups, and you're saying like the execution layer becomes sort of just the settlement layer, do you actually imagine dApps actually still living there? Or do you think they'll all just like migrate off?
dApps are living there now, right? I don't know. Like, I mean, it seems unlikely that they will all immediately make the jump. It feels like we're likely going to see a trade-off where some will just say, well, yeah, I mean, it's expensive, but for me, it's all right. So I'll just stay on the execution chain. I don't see like an immediate transition of everything.
What about like how MEV is treated though? Going back to that question, MEV in a roll-up world where like the roll-up written to chain, and I don't know if there's like advantages for certain things to go faster or slower, if there's like a possibility of a sandwich attack between, I don't think you'd call it that, but between like a ZK rollup and an optimistic rollup, fraud proof, like being written at a certain moment. Like, is this even a space worth thinking about, or is that like completely not?
I mean, I would think that most MEV would be internal, because like the communication between these different systems is asynchronous. Like it tends to be very slow. So I don't know. I haven't.
Yeah.
I feel like there isn't directly MEV that can be extracted from those. I think the MEV is mostly within one rollup. But I think within a rollup, it's exactly the same as it is now. So like each of them will get their own. Yeah.
Yeah, I think that's kind of what we're all understanding now is it's not just an Ethereum. Or like, it doesn't have to just be the main chain. If there is any other sort of like place to do sandwich attacks, people are going to try to do it.
Right. Yeah.
Cool. Well, Dankrad, I want to say thank you so much for coming on the show and walking through all of this with me. Thank you for patiently listening to my kind of Ethereum merge questions, things that maybe I should have known before, but forgot. Thanks a lot for going over all of this with us.
Yeah, thanks a lot, Anna, for having me. And it was a lot of fun. And I thought you had really good questions. So
thanks.
Thank you.
Cool. So I want to say thank you to the podcast producer, Tanya, to our podcast editor, Henrik, and to our listeners. Thanks for listening.